Hello, everybody, and welcome to another wonderful day of physical chemistry. So over the last several lectures, we've built up a Hamiltonian and a set of eigenfunctions to describe the hydrogenic orbitals. And as we've seen, we're able to essentially classify these under several key properties. And three major controlling values have really helped us define our eigenfunctions. So we can define completely our set of orbitals, or our eigenfunction for our Hamiltonian, with three key quantum numbers. And each one of these essentially is going to help convey some very important property of how the electron moves around the nuclei. So the first of which is n. So this is the principal quantum number. And so this is most noted as it controls the energy of the system. So the energy of the electron is going to be entirely dictated by the principal quantum number and the charge on the nuclei. Using these and the empirically derived Rydberg constant, we can get out the energy of the system. Now, there's two things I want to point out is, first of all, this energy is negative, which makes sense because the electron should be trapped in a negative or favorable potential well around the nuclei. The second is something we pointed out before, in that n will also help determine the number of nodes surrounding the number of nodes in the movement of the electron around the nuclei, where the number of nodes is just going to be n minus 1. So if I have an n of 1, I've got 0 nodes. I have an n of 5, there's going to be 4 nodes. Now, this doesn't mean they're going to be radial or angular. There's pretty much none of that information conveyed just in the n. For that, we have to also bring in L. So this is known as the orbital angular momentum quantum number, often just the angular momentum quantum number, or orbital angular momentum. So this is essentially going to tell us more or less the angular momentum or speed of which the electron is rotating around the nuclei. If L is 0, we essentially have random movement. L of 1, I've got essentially a kind of a slow angular rotation about the nuclei. As L gets larger, I have faster and faster movement, and this will also generate more angular nodes. So L will actually give me the number of angular nodes, or essentially how many ways I could more or less take a piece of floss and kind of cut up the density. So if I've got 0, can't really cut up the density. If I have 1 or 2, I'd have to take 1 or 2 pieces of floss to essentially cut up the density. However, this just tells me how many angular momentum, how many nodes in the angular momentum I have. And again, the total speed. It tells me nothing about the direction in which it's pointed. And for that, we go to the magnetic quantum number. So this is our good old m sub L. And one of the reasons it's called magnetic quantum number is because the electron is essentially a charged particle that's rotating in a circle very fast, which means it's generating a magnetic field. And that magnetic field is going to be pointed along the principal axis of the orbital angular momentum. However, we can't exactly detect which direction it's pointed, but we can detect how much of the angular momentum is pointed in the z direction. And that's really what m sub L is telling us, is how much of that angular momentum is pointed in the z direction, and whether it's pointed up or down. And this will tell us a lot about how it moves around the nuclei. If it's 0, it usually means either we've got no movement or any movement occurs around the z-axis, so it's pointed in the xy plane. As the m sub L gets higher and higher, it's going to increasingly point up. Maximizing, of course, with a maximum m sub L of L, because I can't have more of my angular momentum pointed in the z direction than I have total angular momentum, and I can't have more angular nodes than I have total nodes. So n dictates the possible values of L, dictates the possible values of m sub L. And using this information, we can start to build up a set of hydrogenic orbital energies. So we can figure out which one of these orbitals is going to be most likely to be occupied. And using our Rydberg equation with the full set of constants we can get from the formula, what we're going to find is, not too surprisingly, low values of n are going to give me a rather large energy, maximizing at a value of negative of the Rydberg constant. As n goes up, the energy of the orbital becomes more and more positive, less and less favorable. And one of the big things to note is that as it increases, these orbital energies also become more and more tightly packed together. Now, this is often most acutely observed through the ionization energy. So this is the amount of energy it literally takes to kick the electron out of the orbital. So not too surprisingly, this can be given as pretty much the negative, or the reverse sign of the orbital energy. So while the orbital energies are negative because it's a potential well, this means I have to put in a positive amount of energy to kick it out. But otherwise, it's just the reverse sign of the orbital energies. Now, because we are in the world of spectroscopy, it's often useful to try and express these energies as wave numbers. So it is worth noting that this is typically how the book and many other sources do tend to produce the Rydberg constant, is in its wave number form. So again, when making use of your Rydberg constants, please make sure that you you pay very close attention to the units involved, of whether it's going to be in, say, electron volts, which is commonly used with orbital or ionization energies, or inverse centimeters, which is going to be typically given when we're talking more in spectroscopic notation. So in the spectroscopic notation, the Rydberg constant is roughly about 110,000 inverse centimeters, so a rather large number. But one of the reasons why this use of the Rydberg constant inverse centimeters can actually be quite useful is, again, in this idea of absorption spectroscopy. Because what we can do is make use of the difference in between the orbital energies and accounting for the charge of the nuclei and the Rydberg constant in inverse centimeters, we can figure out where that absorption should occur in a classic wave number spectra. And again, as commented previously, one of the absorption spectra that is often most relevant, hydrogen spectra that's most relevant to us, is often what's called the Balmer series, where we excite from the n equals 2 state to the n equals 3, 4, 5, and 6. And one of the reasons these are the most popular is because these end up in the visible spectra. If we are in the Lyman series, we're exciting from a ground state hydrogen, which shows up deep in the UV region. And if we're exciting from the n equals 3 state, instead we see spectra occurring in the IR, or for the n equals 4 in the deep IR. So this is actually fairly useful. And a good demonstration is the beginning peak of the Balmer series, where we excite from the n equals 2 to the n equals 3 state, which shows up at about 507 nanometers. So sitting here roughly in the green portion of the spectra. So one of the big things I do really like to illustrate is that you'll notice that when we're looking at the energy of a hydrogenic orbital, this may seem a little non-intuitive, because the only thing that controls the energy is this principal quantum number. There is no dependency upon any angular component. So it doesn't matter whether L is 1, 2, 3, 4, no difference, just depends on the total number of nodes, because this is giving me the total amount of energy in the system, whether it's kinetic or angular. However, it is worth noting that that L and M sub L tend to tend to play a fairly significant role in terms of degeneracies. So we often want to divide our energy levels, first of all, into energy, our eigenvectors, or again, our wave functions, into energy levels, which are often called shells. And these are going to be dictated on the values of n. So if you're in the lowest energy shell, the first shell, this can be denoted by a capital letter K, followed by L for the n equals 2 state, and M for the n equals 3. And from here on, it goes alphabetically. 4 would be N, 5 would be O, 6 would be P. And again, important to note that all of these make use of capital letters. And this is to help keep them separate from the subshells. So these are based on the L values. So if L equals 0, this is the S subshell. L equals 1, P, then D, F, G. And if these look familiar, this is because we use the subshells to denote orbital shapes, where we have the S, P, D, F orbitals denotes the L, the corresponding L value. And again, by convention, these should always be given in lowercase. Now, when we start pairing together our shells, our subshells, and the individual orbitals, one of the biggest things that we find out is that as I go higher and higher in energy and my n increases, we're going to see greater and greater degeneracies. As I have more possible L and M sub L values. So for example, I have a single degeneracy of the 1s orbital. However, when I go to the second shell, I now have two available subshells, the S with a single degeneracy and the P with a triple degeneracy. So now I've got a total of a degeneracy of 4 on my second energy level, which then goes up to a degeneracy of 9 on my third shell, and all the way up to a degeneracy of 16 on my 4th subshell. So these kind of get a little out of control in terms of degeneracy. Not to mention, our energy levels also become much more tightly packed. So we'll be able to pack more and more energy levels in a tighter and tighter space. So you'll notice that if a system exists mostly in these lower shells, it's fairly easy to figure out where the electron is. But, well, these energies start getting really tightly packed as we get higher and higher up here, till we get into large n values, and you end up forming what is called a Rydberg state. And this is essentially where n is greater than about 20. So these things will fall apart at the drop of a hat, and actually are a good way to probe some rather unique atomic spectra. Now, again, one of the things that's worth noting is that each of these subshells is going to have its own structure. So each subshell will have its own specific geometry. And even within this subshell, each potential value of M sub L may have a different shape. And this is what we're going to spend the next 3 lectures kind of digging into, is the shape of our S, P, and D subshells. So until then, take care.